All right, let's talk about trapped charges and how they modify the threshold voltage. So there's a couple of ways to have such trapped charges, and we'll go through a couple of the details of that. But let's first start thinking about, again, our idealized MOS capacitor and what charges, say, in the oxide might do to it. Okay? So again, just a reminder, this is the idealized MOS capacitor under flat band conditions, and you have a perfect balance between the metal work function and the semiconductor work function. Again, in this plot here, you would have the the semiconductor work function like this, okay? In detail, you typically measure it against the semiconductor electron affinity from the conduction band. I had just reminded you earlier in the section about these expressions that identify the idealized threshold voltage. And now we're going to consider the case where the charge in the oxide is not zero. So in this case here, obviously everything is flat, so there's no charge in the oxide, there's no free charges at all. All right. In actuality, you can have charges in the oxide, and they have been severe issues throughout the technology development of an MOS device. So let's assume that you have some charge in the oxide, then the enclosing fields of that in that region will not be flat. Okay, you will have band bending. Again, this is Gauss's law that points to the displacement field D being zero. The integral of D over some surface is the included charge. So here's the surface, okay? So if you enclose charge and it's a net charge, that means the displacement fields cannot be zero, okay? And therefore the potentials need to be bending. All right, so let's consider, say, a charge distribution that might look like this. And we can integrate that charge over space, and we would do that here to integrate across the oxide. Okay, so you have a charge distribution, a charge density as a function of length throughout the device, and you can calculate that charge. You'll see later in the derivation it is useful to define also the first moment of charge of such a distribution. So the first moment in space would be x times rho x. And you integrate out that and normalize it over the total charge in the system. So that's rho x, and you divide by x0, okay? And so you have in x a value, a moment of the charge, and you can normalize it by x0. That gives you a relative moment normalized to the distance inside the oxide thickness, okay? So there's nothing fancy here yet, just the definition of defining the first moment of a distribution function. All right. Now, that first moment gives you a way to also approximate the charge like this. You could just replace this distributed charge with a delta function of a certain weight. Okay? So you could just say, I'm going to place a delta function like that in the system, and in terms of capacitive behavior, the results that you calculate would be the same. Okay? So, because you'll see in the expressions that we care about, which are the total potential drops, we care about the overall potential drop inside the oxide. We don't necessarily need to know the details of the potential distribution in the oxide. And if that's the case, if we really don't need the detailed curvatures, then we can just replace the charge with a delta function and make our life easier, okay? Obviously, if you did a detailed calculation of the potential as a function of different distributions, you would get different potentials for different distributions, okay? But if we don't care about the ideal differences in the various potentials that you can dream up as a function of different charge distributions, then the delta function will be just fine. And you'll see in the integrals, we'll end up just integrating across the oxide. Okay. So, as a preamble, in a sense, what you'll see is that the threshold voltage will be shifted by this moment of the charge in the oxide, scaled with the charge that is overall in the oxide, in the oxide, and oxide capacitance. Okay, so it's basically a simple shift in the threshold voltage by placing charge in the oxide. Now the details are going to be interesting, and you'll see that in a few minutes. Okay, so Xm is the centroid of the charge distribution. So I just said you can think of it as replacing it with a delta function. Okay, so let's get some pictorial or intuitive view of this, this setup here. So we have a condition here where you can already see from the charge distribution, what is this? This is inversion, right? Because you have a p-doped distribution. You have a depletion region here with Na minus, and you have some electrons that are inversion electrons sitting on this side, okay? And you know it's inversion because this is already larger than the bulk doping, okay? So you have, at the interface, more charge in electrons than the amplitude of the charge of depleted dopants, okay? And that charge is, of course, balanced on the other side by a pileup of, or lack of electrons. So pileup of holes, if you will, and remember we're neglecting any potential drop in the metal because the density of states is very high. Okay? So, what's the electric field that we're going to generate? If we began to either integrate from the left here and perform the integral over charges to get the electric field, you have a linear rise in electric field, then there is no additional charges throughout, so the electric field will be constant, and then you integrate the other way and the other way like this. So you get different slopes at these transition points between charges being, or charges changing in space, okay? So nothing fancy there. And so here is the electric field in the system. Okay. Now, if we place some charge in the middle of the oxide like this, what will the electric field look like when we do this integral? Okay. So let's do the integral now starting from the right. If you do this from the right, you could see that nothing changed from the right. You can integrate up the charge from the right and we'll have the same electric field. Okay, and then the potential, the electric field will be constant, but then you start to subtract charge already in this integral, and then it'll be flat, and then you subtract more. Okay? Makes kind of sense? I mean, again, we're integrating the charges in the system to get the electric field. We've done this now many times in the course, and you can see that placing charge in the oxide will change the electric field, and obviously it depends on the sign of the charge, whether this is a step up or a step down, right? In this case, coming from the right, it's a step down. It's the same charge sign as what we have in the metal, or it's the opposite charge sign of what we have in the semiconductor, okay? All right. Overall, what this does, it reduces the needed gate charges to balance out the overall charge in the system. Because looking at from here, from minus infinity to infinity, in a sense, the net charge will be zero. So if the charge in the semiconductor didn't change and you added a positive charge in the oxide, you need less positive charge at the metal gate to balance out the overall charge. So you reduce the gate charge. Now, what happens if you place the charge at the interface? Let's say we take a similar positive charge, but we now place it close to the semiconductor oxide interface like this. So again, we can do our integral from here, right? Oops, you'll see it. And we will immediately at the interface have the reduce the electric field as we integrate up in the negative direction. Then the potential is the electric field is flat, and you reduce the gate charge again that's needed to balance out the overall charge. Okay. So let's look at some more mathematical expressions like this. So again, we have, you can call it Kirchhoff's law. I have trouble pronouncing the German name in English, so I think it's Kirchhoff in English. So, so here what you do is you balance out the voltages in your system. So the gate voltage must be the oxide voltage, and the semiconductor potential that's dropping off in the semiconductor, right? So again, we're starting out with Poisson's equation or Gauss's law, which is again the second differential of the potential is the enclosed charge, right? Like this. Okay, so nothing fancy here. Now we want to get from the charges to the potential, but we'll do it the other way around right now. We're going to start looking down the integration trail, okay? So how do we get the electric field that's in the oxide, okay? So what we can do is we can integrate the charge in the oxide that's distributed from some value x, say here's the x-axis, and here's x0, and we'll integrate from x to x0. Okay, so we'll start the integral here somewhere in the middle of the oxide or wherever at x, and we're integrating it up to the thickness of the oxide. Okay, so from here we can basically have integrated up this this electric field, and now we have an expression just in the first differential of the potential that's in the oxide. And that's really just the difference here now between the electric field at the oxide edge here minus the running integral, so to speak, in the charge distribution. So that's the field at the oxide, which we know we can figure this out from this point here. And now we're just plugging in this expression here for E at a particular point in the oxide. Okay. So this here is from a known boundary condition that we can bring in. Remember, there is a slight issue with the dielectric constants we need to make sure we keep track of. And now we have we can integrate up this integral here. So we're going to do one more integral across this term, and we end up with a double integral, right? Now, the constant term at Eox, it just gets a distance Eox, and here is now the double integral by just integrating this term here, okay? So we just add an integral over dx, just integrating this, this term here. Now you can show with integration by parts and given the boundary condition that this integral here is the same as this one. And if you look closely, you end up folding in an term x on the inside of the integral, okay? And that starts to look pretty close to this first moment expression. Okay. So here's this integral, which is now indicating the change in the oxide potential. I just transferred this integral from the previous page. You will recognize that you have the oxide capacitance built into the term here. It's just the dielectric constants over the distance, right? So that's just the oxide capacitance, and including another term here of Cox from the previous term. And now we're wanting to integrate this rho, right? Now, we have a definition of our threshold voltage, and that is the one we're ultimately after, right? We're after the change in the threshold voltage due to the built-in charge. Okay, so we know that our threshold voltage will shift by this delta Vox, right? So basically the CV curve is shifted over left or right depending on this expression above here, okay? So all I did is I transferred this expression into here, okay? Now, the term over here, we can identify a variety of elements, right? Remember that we have the total charge is an integral over rho oxide and the moment. And we can identify the term in the dashed line. That's our ideal threshold. And it's being shifted by a moment of the charge distribution in the oxide, which is ultimately just this minus phi m over Cox times gamma n, okay? So if you have a way to determine the charge in the oxide as an integral sense, you know by how much your threshold voltage will shift, okay? All right, so let's interpret this a little bit further. So we have our ideal CV curve again, and now we have a way of placing some charge in a Gedanken experiment into the oxide. So we'll place a delta function of charge into the oxide at position x1, okay? So call this x1 here, and of course we run x here, here's x0, and here is 0, okay? Now, in this case, the threshold, if this is a positive charge, we already identified that then the threshold shift is such that this whole CV curve gets shifted to a lower voltage. This expression here is positive, right? So, and we subtract it from the threshold voltage. Okay, here we go. Now, if we had interface charges, it would be slightly different, right? So let's place some interface charge here and calculate the moment. The moment will be right at the edge at x0. So you're dropping significantly more shift into this into the threshold shift. Okay, so your threshold voltage is shifted significantly further to achieve inversion. Okay. All right. So the shift is larger because really the charge was added at the semiconductor oxide interface. Okay, if we place it at the metal oxide interface, same charge, same delta function, and let's say we place it at first at 0, where 1 is at 0. Well, if that's the case, then there is no correction because x1 equal to 0 is a 0 correction, right? So the threshold voltage didn't shift. So if you have interface charge that sits at the metal oxide interface, it doesn't seem to shift the threshold voltage. So you might say, oh, that's all good then, right? But if you had mobile charges and these charges could wander through the oxide, then and they could wander through the oxide to the other side, then your threshold shift changes significantly, okay? It changes, the whole moment shifts over to the other side and tilts the balance of the voltages significantly. All right, and why would positive charge move to from the metal oxide interface to the oxide semiconductor interface? Well, in this case here, it's positive charge, and it sees a negative charge being piled up on the other side. Okay, so if that charge were mobile, it'll want to go over to these negative charges. It'll be attracted. If these were individual charged particles, so to speak, or atoms that have a positive charge, they will migrate over there. Okay, so that is in reality a real problem. So sodium in a oxide is so small that it can create this bias temperature instability issue that you can read up further. So having sodium in your semiconductor is a terrible thing. It's a small atom, the ion is positive, and it'll migrate through the oxide depending on the bias conditions of your structure, okay? And that, think about it this way, you design a transistor to have a certain threshold voltage and to turn on and off at a certain voltage, and that voltage changes over time. That'll throw all kinds of circuits for an interesting loop, okay? So you really have to manage those free charges. All right, so this is not just a fictitious problem, this has been a real problem. It's been measured extensively. That is one of the issues that had to be overcome early on in the MOS technology to have a clean enough system. And basically, you have a hysteretic behavior in the capacitance, okay? Depending on the bias conditions you exposed your system to, it migrates in voltage one way or another. So as you start from, say, negative voltages here, you ramp up your gate voltage and you measure a certain capacitance. This is actually not a P-type MOS device, but an N-type. So whatever you see here, we've drawn curves that look like this, where we have C and V. And this was for a P-type semiconductor, right? Okay, for an N-type, you just flip these curves around. We haven't done this in the course. Here's an example of such measurements, okay? So as you ramp up the voltage one way, you transition the charges one direction, and then you come down the other way. Okay. Okay, I was just thinking, is sodium positively ionized? Yeah, it is. So you have a bunch of positive charges that might be sitting at the MOS interface, and maybe they start out at the metal interface, and after a certain time, these charges have migrated over to the semiconductor side, and they will have shifted the behavior of your CV curve. Okay, so threshold shift can happen due to trapped charges that are in the oxide, and those trapped charges can be mobile, and that'll shift your threshold voltage significantly. And we just calculated a term here that has the moment of those charges implicitly or explicitly as an expression of that threshold shift. Okay. So in the next section, we're going to talk about the physics of interface traps and how they might modify the threshold voltage as well. So I'll see you in that section.